Greetings to everyone watching. I, Manvi Jain, take this platform to discuss the topic quantum Zeno features of bistable perception, which is a derivation of quantum cognition. The introductory picture shows a watched pot which never boils. This is an example of quantum Zeno effect. Let's first discuss the quantum theory, which is a logical consequence of some rather simple and plausible basic assumptions on the nature of observables and states of physical systems. Since very early days of quantum theory, it has been entertained that quantum theoretical concepts like complementarity and entanglement might be meaningful and important even beyond the realm of the physical world in its strict sense. This notion forms the basis of weak quantum theory in other parts of science. Weak quantum theory, a derivative of quantum mechanics. The notions of systems, observables, and systems remain unchanged. Observables are identified with functions mapping states to states. This emphasizes the importance of observables as representing active processes with the capacity of changing states, which is vital in quantum theory. For instance, the significance of complementarity and entanglement could be explored in philosophical, psychological, or even psychophysical problem areas without losing the desirable formal rigor and precision. With this notion, we take this opportunity to discuss weak quantum theory in cognitive sciences. So quantum behavior or quantum-like behavior being present in complex internal organizations has an example of cognitive system and its neural correlates in the brain. And here we intend to apply the framework of weak quantum theory to another scenario of cognitive science, the bistable perception of ambiguous stimulus. The figure alongside is an example of such a process. This is a vast perception example wherein a perceiver can perceive this image as either two faces or a vase. And this bistable perception can flip over with time. This is the basis of bistable perception, which arises whenever a stimulus can be interpreted in two different ways with approximately equal plausibility. A very simple and often investigated example of bistable perception is the so-called Necker cube, as can be seen in the figure alongside. This is a simple cube, the stimulus. We propose to describe bistable perception with the formalism of the two quantum state system, where the two basic states correspond to the two different ways to interpret the visual stimulus, that is the cube. As can be seen in the picture below, there are two types of states that can be perceived in only one type of stimulus shown above. The switching between these two different perceptual states correspond to the quantum transition between the two states, which are eigenstates of the operator, representing a particular perception and unstable under the time evolution of the system. Psi 1 is plus ket and psi 2 is minus ket. These correspond to the two eigenstates of one particular operator. Let's briefly discuss quantum Zeno effect in principle. We consider a quantum mechanical system with a state space spanned by two states, psi 1 and psi 2, neither of which is an eigenstate of the Hamiltonian H, generating the evolution matrix. This particular equation represents the time evolution of a particular state with respect to time. If the system is initially in the state psi 1 and allowed to evolve freely according to ut, then its state will oscillate between the states psi 1 and psi 2. This oscillation can be slowed down by increasing the frequency at which the system is measured, asking whether it still resides in its initial state or not. In the limit of continuous measurement, the evolution of the system can be completely suppressed. This phenomena is known as the quantum Zeno effect, which was originally discussed by the quantum Zeno paradox by Mishra and Sudarshan for the decay of unstable quantum systems. QZE or quantum Zeno effect in Necker cube experiment can be discussed in the following way. In the experiment with Necker cube, a cube is observed with free flow of perceptual states. In special cases, measurements are taken. In this regard, measurement is considered as the mental process determining in which way the figure is perceived. The variables that are involved in this particular experiment are delta t, which is the time between successive observations or measurements. As a lower bound for delta t in cognitive operations, the so-called order threshold of about 30 millisecond is proposed. So from the view of cognitive science, the amount of 30 millisecond is important, since we also experiments have also shown that 30 millisecond is the least amount of time that is important for a visual experience to be taken place in the human brain. That is, if any visual stimulus is presented for a time between 0 to anything less than 30 millisecond, the visual stimulus is subliminally perceived and not liminally perceived. That is, the person cannot identify the presence of that particular visual stimulus. Hence, it's an important time period. Thus, here in this experiment, delta t is taken as 30 milliseconds. T naught, the oscillation period for the switching process between two non-stationary states under the unperturbed evolution of the system. And T is another variable, which is the increased switching period for the case that measurements are carried out, and the results in this regard will be discussed up further. The calculations involved in this experiment are, as we have already discussed, the two different eigenstates that can exist for the two particular states transitioning between the two. In this model, delta t defines the time interval between two successive observations, and t defines the time scale after which the state has changed with 50% probability. It is assumed by experiments that t by delta t equals n will always be greater than 1. These quantities can be related to the evolution of the system under the condition that no observations are performed. In this case, the time evolution is given by ut, which is the time-dependent equation of evolution of states, and as mentioned above, the state oscillates between the two eigenstates and with period of t naught equals psi pi by 4g. This leads to the relation as can be seen in the given equation by preceding calculations. The conclusive statement in this particular experiment, after skipping many calculations, we can say that the quantum Zeno model establishes a relationship between these three time scales, that is delta t, t and t naught, where t naught will come out to be 300 millisecond. T naught will be increased to t if measurements are carried out in this sense. For delta t is greater than 30 millisecond, which was taken as 30 millisecond as previously discussed, and t is equal to 3 seconds under the condition of continuous stimulus presentation. Such a value of t naught is often discussed as the approximate size of the time interval after which the processing of sensory inputs leads to a consciously available result, that is a mental representation of the stimulus. In such types of examples or such types of studies, several studies have found that neurocorrelates of such states for the first time were reported to be an early component of 250 millisecond, which is around 300 millisecond, another time period which is of importance to the cognitive state of visual perception. Further experimental material will be needed to firmly establish the cognitive relevance of the quantum Zeno time scales in future. Hence, there is an important or an essential need for many studies to happen in this field. Thank you. That's it for this topic.